Any questions? So I have revised the notes, not in content, but just a little bit in terms of organization, but I'm not uploading it now. What I'll do is I'll wait till the chapter is over, and so when I start chapter 3, you should have the updated chapter 2. But you have the effective, content in there, just the way I organize sections. So when you look for the sequence of my lectures and notes, they may not match up entirely. It's not like it's a huge change. Any questions so far? And so what we decided was next Wednesday, you will have an in-class exam. Okay? So today's Monday. By Friday, I will tell you the content of the exam. Okay, so today I want to, if I should give a title, it's called the Lorentz group. We've talked about Lorentz transformation. So, and we know that at the moment at least, if you have a vector A, it transforms by a matrix. And we know what works. We know translations, because space and time translations, because vectors are not affected by that at all. And then we know there's rotations and boosts, correct? So we've done boost in x-axis, and clearly we don't expect a problem with any other axis. Now the question is, well, are there anything else that we're missing out? So we do this in 2 stages. The first stage is, we'll still assume it's a matrix. Okay, so if you can pick an arbitrary matrix where speed of light is preserved, are we missing out on anything? But we'll do a slightly more stringent condition. At the end, as I mentioned before, I'll hearken to Zeemann's theorem where we'll have a larger reach. But at the moment, we're going to say, forget just the speed of light. But what if we want the inner product to be preserved? So given 2 vectors, A and B, so it can be AX and BX, they're at the same point. The inner product of these guys are what? You've seen this before, A0X, B0X plus all the other spatial components. All the spatial components are positive. So we want this to be preserved under a matrix transformation. Okay. Now, the official, what I'll be doing is theorem 2.6. So what we want is, I'm not going to write the entire sentence, but this is at some point x. We don't need to specify it. It's at any point x. So suppose I want to be equal to if I take the inner product of 2 vectors using this formula, and then I pick any matrix transformation like this, and I take the inner product using the same formula. It's almost like while vectors can transform, the expression for inner product does not change, correct? So if I do it in one basis or the other, the inner product should be the same. If this is to happen, if and only if, this lambda has a condition, and we'll write it in a matrix notation. If eta is equal to the transpose of lambda, eta times lambda. That is the statement, and this is the proof. Is it clear why we're doing this? I mean, the rest, all of this is just algebra. So what's more important is why are we doing it? Why does it fit in? What am I saying? If you take two sets of observers and you have two vectors in one frame and then you transform the two vectors, you get in the other frame. And you compute the inner product of these two vectors using the same formula. Using this formula, right? Regardless of the frame. See, it's the same formula, same eta. You're going to get the same number. Yes?
We've already established that lambda transpose times lambda is equal to the index, or not to the identity. Yeah.
Correct.
So isn't that just saying that eta is equal to eta no matter what?
No, because how do you bring this lambda transpose to that side?
You invert it. No, you don't invert it.
And we don't know you can invert it. We don't know the formula for the inverse of lambda. It's easy to find for rotations and boost along x-axis. But more than that, the question is there anything else? Right? Is there a new kind of, the answer is no. But is there any other kind of things that we haven't called, named, that could be hiding in here? Okay? So what we'll do is we'll start with this side. This side can be written as what, I have to be careful of the index. I chose alpha, beta, A alpha, B beta. That is this side. Okay? Now what I'm going to do is I'm going to write this part. And I'm going to use mu, and you will see, you're asking, and this is good to even see how we do things, A and B. First of all, does this bother you that this is alpha beta and that is mu? You have to get used to the word dummy index. They're just being independently summed on, correct? First of all, when I write alpha down and alpha up, what do I mean? You're doing sum over all possible values of alpha. So I could write, but I'll write it and I'll erase it. I could write this from 0 to 3. But this means exactly the same as without this. That is the Einstein summation convention. Okay? Now what I'm going to do is get rid of the bar so that I can see what happens to all the matrices, A, mu, and when I get rid of the bar, I would have lambda mu alpha and lambda mu beta A alpha B beta. Is that correct?
So that's saying that you're translating from
yeah. So I'm
mu to
right,
beta,
right. No, I'm getting rid of the bars. How do I get rid of the bars? I deploy this guy. And so, thankfully, I had alpha beta on both sides. So now alpha beta, A alpha B beta. This is equal to mu lambda mu alpha lambda mu beta A alpha B beta. This must be true for any alpha and any A and B. Any and all A and B. How is this possible? You can pick all combinations of A. You can pick A to be just 1, 0, 0, 0, and B to be 1, 0, 0, 0. And then you can pick A to be 1, 0, 0, 0, and then you can pick B to be 0, 1, 0, 0. So when you work out all those combinations, the only way this can work out, and I want you to convince yourself of that argument later on this evening at home. The only way that can happen is if this is equal to that. So we must have that eta alpha beta equals eta mu lambda mu alpha lambda mu beta. That's what you have. Now, another thing about this Einstein summation convention is that you can write, this is not matrix multiplication. We have written an explicit formula what terms get multiplied. I can move these things any which way I want. But matrix multiplication, A times matrix B is not the same as B times matrix A. But these are just numbers. So what I can do is I can move this over here. I can move anything anywhere. Now look at this. This is matrix multiplication. How do you multiply matrices? Outer and inner. Is that clear, everyone? Yeah? But look at this. This is inner and inner. So what do? I can write this as transpose and then replace this with alpha mu. Correct? And then I have beta, mu, beta. So now I'm going to write it as matrix multiplication, and we have our result. So all inner products are preserved only if the matrix lambda satisfies this expression. I just need a question or two just so that I know that we are anchored.
So you're getting rid of the indexes on there because it's matrix multiplication?
Because it's matrix multiplication, with the understanding that it's matrix multiplication.
I'm kind of confused because you've got two etas.
Correct.
Beforehand they're different because there's eta alpha beta,
Yeah.
and then eta mu nu.
That's a good question. It's a fair question. When I say eta alpha beta, eta mu nu, is there a difference?
Not necessarily.
It depends on value of alpha and beta. If I pick alpha and beta to be 0, then I'm getting eta 0, 0, which is -1. If I pick mu nu to be 0, 0, it is eta 0, 0, which is -1.
But in that case, it's just all it says for that equation is that it looks like they're equal to each other, or like the etas have some. They should be equal to each other because they're the exact same symbol.
They are equal to each other.
Always?
Yes.
Necessarily.
Eta. Yes, in special relativity, eta is this matrix. That is the whole point, right? We're trying to preserve the inner product. And the inner, so let me make that very clear. By this, I mean minus A0, B0 plus A1, B1 plus A2, B2 plus A3, B3. That happens only with this matrix.
I forgot the fundamental.
Yeah, that is our anchor.
Yeah, that makes sense. Got it.
Yes, David.
So like for the eta, is it just like outside the ones, it's just filled with zeros, right?
Yeah. These guys are all zeros.
I want to make sure I wasn't writing something wrong in my notation.
Okay. So we still don't know if we have gathered new friends. Are there, additional lambda? Well, we just know it has to satisfy this object. So that equation becomes very important. It's an anchor for us. It tells you, if it satisfies this, it satisfies this. And I wrote if and only if. You can write the theorem backwards to get the same result because these are all equalities. Yeah. Okay. So I'm going to name this object, And as always, I want to write complete sentences. So this is definition 2.4. Again, definition 2.4 in my, I don't think this may have changed, but it's my new numbering. But any lambda that satisfies this, okay? So any lambda that satisfies this property is referred to as a general homogeneous. How do I spell homogeneous? Or homogeneous. Lorentz transformation. Right? So whatever this lambda is, we're going to call it the general homogeneous Lorentz transformation. That's just naming it. So we can call upon it very easily, although it's not so easy to write general homogeneous Lorentz transformation. So there are three problems here. I want to state them so that we know the context during the rest of the class. So problem 2.5, is to show that boost is a general homogeneous Lorentz transformation. I mean, they all better be. Rotations, all of that better be. Right? Boost is a general homogeneous. This is a problem. You'll have to verify it. You have to pick a boost. I mean, again, at the moment, we just do it along the x-axis. You have to convince yourself that this formula is true. Then I'm going to call, this is the next problem, sort of an uppercase sort of, I don't know what they call it. This is in tech, it is math BB. Have you looked into tech yet? This is the font. Yeah. This is the matrix. Why this uppercase T? It's time reversal. And guess what time reversal looks like? Oh, not quite. Yeah.
Almost beta.
Oh, sorry.
Oh, it is beta. So it is beta.
Yeah.
Well, it's time reversal. That makes sense. It's just
Yeah,
it's literally just inverting time.
Inverting time. But oddly enough, it is a general homogeneous Lorentz transformation. It's kind of neat. The other one is the same thing, parity. What does parity do? Keeps time intact and reverses space. Flips the spatial direction. This is also general homogeneous Lorentz transformation.
Conceptually speaking, okay, actually, never mind. I was about to say something obvious.
Go ahead.
I was just going to say, like, those two just visually, like, their transpose is just equal to themselves. So it's just, you're multiplying it by itself.
Correct,
But
correct.
the thing is, they're only reversing things, so it's just reversing and then unreversing.
Unreversing, yeah.
So it's like, it's literally just
So if you do it twice, you get identity. So for example, t squared equals identity equals. Furthermore, listen, t is exactly this. So if lambda is eta, eta is its own inverse. Eta times eta is 1. This is eta transpose, which is eta, which is eta. Yeah, all these things sound trivial, but there's a big meaning to it. Okay. Okay. Now, let's again talk about the determinant of. So you know, if I take a general Lorentz, a general homogeneous Lorentz transformation, it satisfies this equation. Let me take determinant on both sides. What's the determinant of eta?
Would just be
Minus 1.
yeah, next one.
So, and the determinant of the product is product of the determinant. So this is det lambda transpose. This is minus 1 det lambda. But we talked about how these two guys are the same. Once again, we get because the determinant of the transpose is the same as the determinant of the original matrix. And I'll say it one more time. What is plus or minus 1 not equal to? 0. So that means you're able to invert this matrix. That means lambda inverse exists. Okay. The next, it's a theorem. Again, these are not so complicated, but it's nice to classify this and label it. We give you a formula for the inverse. We know the inverse exists. So if you have a matrix whose determinant is non-zero, the inverse of that matrix exists. And in my new nomenclature, this is theorem 2.7. And I'm going to define this guy. What was the original lambda like? Let me call it alpha, beta. The first index was up, the second index was down. Here what we have done is the first index is down and the second index is up. You will soon see what that means, but I'm going to say the same thing differently. In this guy, the first index has been lowered and the second index has been raised. Lowering and raising is done with eta, an inverse of eta. So let me show you what that means. I need to make sure I pick u beta, beta alpha. I'm going to write it this way just to be difficult. So first of all, look at this. I sum beta, so the beta is gone away. When you sum it, it's gone away. What remains is nu. Sorry, and nu is a lower index. So whatever we have here has the first index that has been lowered. This index has been lowered. This is not quite matrix multiplication, is it?
So alpha is not a subscriptive lambda?
It is. Alpha is a subscript of lambda.
Like
Lambda has two subscripts, right? So here, alpha is being summed. Could I have written it as alpha mu? Yes, because eta is a symmetric matrix. It has only diagonal terms. 0, 0, 1, 1. 1, 1 is the same as 1, 1 the other way around. Yeah? I could have just as easily written it, and then it'll look like matrix multiplication. But for some reason, I wrote it the other way. So since I don't want to mess up, I'm writing this way. Okay, so that's fine. So the claim is this. Alpha, this is the claim of the alpha inverse. Because, we know its inverse exists. And if an if lambda is an object like this, its inverse should also be an object like that. And here's a formula for it. Isn't that neat?
So it is genuinely just the inverse?
That is, we'll prove it. That's the claim of the theorem. I have to prove it. So if I have this lambda, because remember lambda can be complicated. It could be boost about a weird direction followed by a rotation. So it could be a complicated matrix. But as long as it satisfies that general homogeneous Lorentz transformation equation, I know how to do the inverse. I don't have to worry about formula for inverse. I just back it up. Okay? This is easily done. Okay? So what I'm going to do is begin with what I know to be the inverse. That is equal to, oh, right. What do I know this? Yeah? So I'm going to multiply by lambda inverse on both sides. Correct? Then I'm going to multiply by eta on both sides. What is eta times eta?
It's just index.
Minus
sorry.
111 times minus 111, matrix multiplication. We just said eta is the same as the time reversal operator.
It's just
And then we said t squared must be
this is the index.
Not-
Not the index. The
Identity.
Jesus,
Identity.
I just keep getting the words mixed up.
So here's the formula. Yeah? Okay, well, let's just write it out then. So lambda inverse mu is eta lambda transpose eta mu. Okay, so this is lambda transpose. This transpose is a matrix object. It doesn't do well with our indices, with the Einstein summation convention. We'll get rid of it very quickly, don't get me wrong. Yeah? By the way, all this index manipulation, what we're secretly doing is tensor calculus. So we're just an inch away. So tell me if this is correct. Let me write this down, alpha, beta, and then this is eta mu alpha lambda transpose alpha beta eta beta mu. Look, if alpha is multiplied, these two are multiplied. If beta is being summed, these two are being summed. Now, why did I have to put summation?
Because alpha's not being summed inherently right there.
If I didn't put the summation symbol, I should not see summation. In fact, I should be puzzled.
Because alpha's only ever up.
It's only ever up.
There's no down.
Remember, summation is one up, one down.
Same with beta.
Same with beta.
Yeah,
Same with beta. But that's easily cured in the next step. So then I'm going to write this for now, and then I'll erase this. Beta alpha. Now, are they up, down? So what can I do? Get rid of it. Summation is implied. Not that summation goes away. Summation is implied. Oh, what is that? What am I doing here? I'm lowering beta and making it nu, and raising alpha and making it mu. That's precisely the expression there. Now you're telling me, wait a minute, that's not the same. And that, the first couple of times you do these index manipulation, you want to make sure you understand it. Well, it's sort of the same. First of all, this guy's being moved over there. Does the ordering matter? When we have summation implied by the double summation. Secondly, this is eta nu beta. What do you have over there? Beta nu. Why are they the same? I just answered this. They're symmetric. Yeah.
Switching around is
breather. There's a lot of notation involved here, right?
switching around is okay because in this case we're not doing matrix multiplication, we're doing summation.
Correct.
Okay.
Correct.
Because if matrix multiplication, you can't just.
No. See, so yeah, let me answer all the questions here. But typically, how would you write, if you're doing matrix A times matrix B, you would write, if you didn't take relativity, your notation would be M, N, then B, N, and L. And the summation would be over N. Outer, inner. That's what it is. And this is the object, ML. The ML component satisfies this. Right? But this, if it is like this is implied. And then if you write it in any order, the number for each ML would be the same. Because this is a number, that's a number. 3 times 2 is 2 times 3. Or 3 times 2 plus 1 times 7 is equal to 2 times 3 plus 7 times 1.
Oh, because the indices indicate which index you're summing.
Which order you're doing it.
So it completely gets rid of the idea of you can't switch the order of matrix multiplication. Because in this case, you are doing, you're still doing matrix multiplication, it's just that you're summing instead of
Summing, yeah, you're writing explicitly a formula.
Gotcha.
So just because you write it back and forth, you're not changing its value. Noah, are you convinced?
As convinced as I can.
No. Either you're convinced or you're not convinced. I can help you get there. Not necessarily today. This is. Let me ease your worrying mind. This is only notationally cumbersome. Let me make it difficult for you. The worst kind of difficulty is notationally cumbersome, because you don't have to learn. You'll miss out on the idea because notation can be debilitating. So you can ask me questions periodically. You can ask me questions periodically, but any questions?
What's the subscript by the A dot B?
It's ML.
ML. Yeah.
And what if it's not symmetric? Is it ever not symmetric?
Is what not symmetric?
Like the M and N, for example.
Oh, here it's not symmetric. These are any matrices A and B.
Oh, okay.
Yeah.
This doing the summation like this removes the necessity to keep things in the same order.
Yeah, I would recommend, gosh, if you're easily convinced, I would recommend make up your own 2 by 2 matrix and try it out. And then if you say, well, that just worked out too easily, knock yourself out with the 3 by 3. And then if you're really penitent,
No.
if you do 4 by 4, we're good. Space-time ends, this is not string theory. Our dimensions end with 4. Okay. Do ask me questions on that one. I get it. It can be difficult. There's a theorem that I would like for you to read on your own. It's just like this. Let me state its meaning. Theorem 2.8. It just says eta mu nu equals lambda mu alpha, lambda mu beta, alpha. I provided the proof. Okay? The same kind of index multiplication. Partly I'm doing it because I want you to fight that proof on your own. There's nothing more to it. It's an exact same calculation like we just did. It's in your notes, but fight it on your own. do fight it, because then you'll have to confront an explanation, and then even this becomes. So I missed the notation that I could have possibly mentioned ahead of time. Go ahead.
Is there a visual difference, like in the matrix, that is lower notation instead of upper notation?
What does that mean?
So, like, if you have an eta
Mm-hmm.
with an alpha beta on the bottom, right?
Alpha beta on the bottom.
Yeah. Is there a difference between that and an eta with an alpha beta on the top?
Typically, yes. But in the case of eta, there's no difference.
Because it's transposed.
No, because how did I inverse eta with, how did I define this? Good. I like these questions because it's really notational and you have to keep track of all of this.
Like that definition right there.
What is the definition of eta with indices up? It's the inverse. Coincidentally, the inverse of eta is eta.
Okay. So if the index is just on the top, it's the inverse of eta?
Inverse is just on the top. It's the inverse of eta, correct.
Okay.
Which is eta.
Okay.
Altogether confusing.
So if another matrix that isn't eta
Yeah.
is written with the indices on top,
Yeah.
that just implies it's the inverse of the original matrix.
No, it doesn't. Suppose. Yeah. Listen, this is the thing, right? Suppose I write, I don't know, these are, you'll see that very soon they're tensors, right? If I write this. And then I write another object. Now you're inclined to say that these are inverses of each other, but let me tell you, this is not the whole story. What if I do this? What is inverse of that? We'll have more, right? So this, you can consider one, two. This is the lowering of that. Or equivalently, this is the raising of that. If I were to, okay, this is way ahead of the story, but since you asked me, I'm just going to say, if I have this, I can do eta mu, and I lower this. Then eta nu, and I lower beta. This is ahead of the story. You lower things by eta and its inverse.
And you also raise things?
You rate it, and it's inverse, yeah. So I can even do, listen, I could do this. If I did this, what would it be?
Mu and then, beta would be on top.
I can bring it up. Tell me, what would it be?
That one would be, oh, it'd just be T alpha mu, or mu alpha. Oh, no, sorry, alpha, wait, no. Mu beta. Would just be
Where
T,
is
on
the
top.
mu on the top?
Yeah, and beta on the bottom.
Yeah. That's the sort of tensor gymnastics that we're going to get into. But it's a good thing to keep in mind.
But eta itself can also be acted upon.
Eta itself can be acted upon by eta. You can only lower things by eta.
Okay.
Oh, that's also interesting. Suppose I try to do this. What is that?
That's the, what's it called?
Very good, Gracie. Yeah.
Oh, conquer delta. Oh, because of the fact that eta is negative 1, 1, 1,
Yeah,
1,
so-
it comes a Kronecker delta.
Well, this is the inverse.
Yeah.
So when you multiply Kronecker delta, so when you multiply a matrix and its inverse, you get the identity. Equivalently, I could write this as,
Okay,
I mean,
so you can just say.
because what have I done? I've taken a nu and lowered it to alpha. So if I write this, I really mean that.
Let me bring that up.
We're going off the beaten path.
Yeah, that's good to know.
Yeah.
I'm so glad you understood what I was trying to say.
Got it this time.
The thing.
You do this periodically. Like, you sit there, in a days, and then periodically you just shout out the right answer.
I can't tell if that's a compliment or not, really.
It's always underhanded, right?
Exactly. Yeah.
That means if
Well,
she
like
pays
sometimes-
attention, she could do it more often.
Sometimes, no, I do pay attention. Sometimes, like, I'll have the right answer ready to go, and then Jackson will say it. He needs to
When you
hesitate
do
more.
no.
You need to hesitate more. Give
No,
someone a chance.
because like,
Start throwing stuff out there.
yeah, if you have the answer, throw something
It
in.
just takes
But on
place.
Wednesdays, you never answer because you're dreaming of fried chicken.
Oh,
This
yes,
is true.
100%.
I'm with you. So, actually, I get more excited about the bread pudding there. So, anyway, so we talked about, oh gosh, I need to make sure. Please verify that this is correct. This is the equation I said, where lambda would be referred to as a what? General homogeneous Lorentz transformation, right? Such a lambda, this lambda is all such lambda, what does this mean? Belongs to a group, right? A set of things. It's called, the symbol for that is a script L. So that's the general homogeneous Lorentz transformation. And this, of course, in LaTeX is slash cal. Okay. Yep, problem 2.8. Again, I'm not doing it, but I'm stating it. Show that L forms a group under matrix multiplication. So what do you have to show? Show that identity belongs to this. And that's easy enough to show. You have to show that if lambda is an element of this, lambda inverse is an element of this. Correct? A group should have the identity element, the inverse element. What else should be true? If I take two elements of the group and I multiply them,
It should still be a part of the same group.
it should be part of the same group.
What is that called?
Closed under multiplication.
Does it have to be multiplication or can it just be addition?
Whatever the group multiplication is. In this bag of matrices, when we say multiplication, we mean matrix multiplication. So you are getting a little bit of practical group theory for free. Some of you have had, courses on group theory. Yeah. So this is totally worth doing, right? Huh?
We were all in mathematics except for Veronica.
Yeah.
So special.
Yep.
Yeah, you know what, actually, the next week I want to talk about a nice result, and I can possibly end this section, so I'll wait till, when I try to pack things, too many things in, it just runs into each other. I've noticed that the first couple of lectures, I just tried to pack way too much material. Let me turn the camera off, and I can take any questions you might have.